So for the second part, guys, in 6.1, what we want to do is we want to find the position of a particle or an object at a certain time given an initial starting position and also the velocity function. So what your author gives you here is a formula for how to go ahead and calculate that. What I want to do is I want to walk you through why this formula makes sense, okay, and then I'll go ahead and show you how to apply this. So let's say, for example, that we have a velocity function. Oh, I don't know, I'll make something up here. We'll say the velocity as a function of t is equal to, I'll use that same one that I used last time, negative 2t plus 4. And then let's also say that a function's initial position, so the position at time 0, that's s of 0. Let's say that that's equal to 10. Okay, feet or whatever it happens to be. I'll put feet in here. So this will be in feet per second. Okay? It's really irrelevant, the units here. The idea is this. Let's say, for example, that we have a stretch of road like this, and we've got a person on it, and they start at an initial position. Here's 0, okay, and here's 10 feet down the road. And so at time 0, they've started at 10 feet. Now, the question is, how do we find their position along this road given this velocity function at any given time? So let me walk you through an example with just some numbers first. So let's say, for example, we want to know where is the person at, where is the individual at t equals 3 seconds. Well, here's what we need to do. We need to figure out how far the person's moving in 3 seconds. So what happens to them? Okay, so clearly, from the last example, they're going to move out and then they're going to come back a little bit, right? And so what we do is we take the initial position and we add it to the displacement. So the displacement is from that initial time 0 to whatever time we're looking at, and here we're looking at 3 seconds, the velocity function, like that. Okay? This is equal to the position at time 3. So the position at 3 seconds is equal to the initial position plus the displacement. So if we go ahead and we calculate that, we know the initial position is 10. And now our displacement is from 0 to 3 vt dt. And so let's go ahead and compute this guy right here. So that's the integral from 0 to 3 of negative 2t plus 4 dt. So we'll work on an antiderivative here. And so we know that that antiderivative is negative 2t squared over 2 plus 4t plus the constant of integration. We're going to evaluate this using the fundamental theorem of calculus between 0 and 3. So this, again, this is going to take us to t squared, negative t squared, plus 4t evaluated between 0 and 3. So that'll give us, if we work this guy out, which is really this piece right here, that'll give us negative 9 plus 12, which is 3. So what happens is the guy moves 3 units to the right. This is the overall displacement. So we take the initial position plus the displacement, and that gives us the position of the person at 3 seconds. And so even though the person walked this way and then came back, what we have is they traveled a displacement of 3, and so now they're at 13 units at time 3. Okay. So let's go back. Oh, actually, so let me go a little bit further on this before I go any. So let's select this area and get rid of it. We don't need that anymore. Whoops. Let's get rid of this guy too. Okay. Now what if we didn't know the time? Let's say t was equal to some unknown time. We'll call it a. So what we want to know is, what is the position of the person at time a? Well, that is still equal to their initial position plus the integral from the initial time to the time a of the function vt dt of the integral of that. So this right here, so this is a new function, okay, that's dependent on this right here. And so what we need to do is we need to get antiderivatives first of all. And you can show that these are actually equal to one another because the antiderivative of vt is s. So this will give me s0 plus this right here. Because vt is the derivative of s, the position, we have s at a minus s at 0, because these are the antiderivatives evaluated at the endpoints. And so if you simplify this, look at that, you just get sa. Okay. So again, the idea is to take the initial position, add it to the displacement, and you get the overall result of where your object ends up. So let's go ahead and work an example. So example number 2 says that you have a block that hangs at rest from a massless spring at the origin, which is position would be 0. At time 0, the block is pulled downward 1.4 meters. Okay, so that's this picture right here. So it's down 1.4 meters, and then it's going to be released. Okay, so what it's going to do is it's going to bounce up and then down. So watch. It'll go up and then down and come back up, and it's going to oscillate. Okay, and it's going to oscillate according to this function up here. So this is the velocity. Okay, and we'll assume that the upper direction is positive. Okay, so let's go ahead and stop that. It says find the position of the block for t is greater than or equal to 0. So let's go ahead and take this function. We'll play around with it a little bit. Actually, what I'm going to do here is just split these screens. I don't like how small that is. Let's not do that. Let's just bring it whole. Okay. We'll just go back and forth. Not a big deal. Okay, so what we have is the following. The velocity of the block is going to be equal to this function right here. So 1/4 sine t. For t greater than or equal to 0. This is the velocity function. So clearly it's oscillating, right? Now the initial position of the block is at negative 1/4 meters. So if I want a function that describes where the block is at any time, let's say at time, they probably say time something. Let me look here. Find the position of the block for t greater than or equal to 0. Okay. What I'm going to do is the position at time t is going to be equal to the initial position, s at 0, plus the integral from 0 to t of the velocity. Now velocity, t is a dummy variable, so I can replace it with whatever I want. So I'll do vx dx. I don't want this t to be the same as this guy in here. It becomes confusing. Okay. If you want to use a different variable besides t, you can, but this guy right here needs to match this guy right here. Okay, because that's the function, that's the piece that's changing. Now we know v of x. Well, we know vt is equal to 1/4 sine t, so v of something should be equal to 1/4 sine something, like that, right? Because that's how functions work. Whatever you plug in here is what you see over here. And so for something greater than or equal to 0. So this is kind of the generic of this. Okay, so we get this right here. And we just need to make sure that this variable right here matches the dx piece right here. Now what we have is we have a function to replace this. So vx integral from 0, whoops, that's supposed to be a plus sign, not equals. So 0 to t, this is a t, not a plus sign, Now Vx is 1/4 sine x dx, like that. So this is the position function right here. So S0 we know is negative 1/4. Okay. Now here we need to find an antiderivative. So what I'm going to do is I'm going to pull out the 1/4 because it's a constant. Well, it's a, yeah, I mean it is. It's, well, I shouldn't say it's a constant. It's a it's the coefficient, right? And so when we have a coefficient out in front, we can go ahead and bring that out because it's like a scalar, right? So this is going to be sine x dx. Now we need to go ahead and evaluate this guy. So this is, well, the antiderivative of sine is negative cosine x, and we need to evaluate that between 0 and t. So this will be negative 1/4 plus 1/4 times negative cosine t minus negative cosine 0. So this would be equal to negative 1/4 plus 1/4 times negative cosine t plus cosine 0, like that. So this will be negative 1/4 plus negative 1/4 cosine t plus 1/4, like that. Right, because I got 1/4 times, this guy's right here is 1. So negative 1/4 and positive 1/4 go away, and I have negative 1/4 cosine t. That is the position of the weight on the spring at any time t. So for example, if I want to know what is the position of the mass at time, let's say, oh, I don't know, I'll use something nice here. Let's do pi over 3. This is roughly 1 second, right? Pi is 3.14 divided by 3, so roughly 1 second. The position of the weight at 1 second, the position at pi over 3 to roughly 1 second is equal to negative 1/4 times the cosine pi over 3. And so that'll be negative 1/4, and the cosine value at pi over 3 is 1/2, and so that will be negative 1/8. Okay, so let's go back and make sure that we're answering some of these questions here. So the first part is find the position of the block for t is greater than or equal to 0. So that's our function s of t. So let's go ahead and we can check the solution here. And what I want you to notice is that we get, for an answer, in both cases, we get s of t is equal to negative 1/4 cosine t. So if we go back and we look, we got negative 1/4 cosine t. There it is. The second question says graph the position function for for t between 0 and 3 pi. So what I'm going to do, you can use your graphing calculator if you want. Let me move some stuff around here. I'm going to use Desmos to graph this. So the position function is this guy right here. So what I'm going to do, go to Desmos. Launch the calculator. And so I've got y is equal to sine x, negative 1/4 cosine. So this right here, this is the position of the block. So at time 0, the block is at negative 2.5. The velocity pulls the block up. At pi over 2, it's at a height of 0. At pi over 2 seconds, it's at a height of 0. At pi, it's up at a height of 1/4, so it's going to go from negative 1/4 to positive 1/4, down to negative 1/4, back up to positive 1/4. And if I want, I can change my x-axis to go between 0 and 3 pi. Just type in pi, and let's do this by pi over 2. And so what we can see here is between 0 and 3 pi, this is the position. So the block starts down, moves up, which is correlated here, then it moves down, and then it moves back up. So this is the pattern of the block. And if we go back, the cool thing about your book is we can watch this. We can watch this occur. So here in the black, I've got the position. Okay, now notice, look at this function. We go down, up, down, up. Let's go back to Desmos. We start down, up. It's exactly what we just saw. And in fact, if I go between, let's say, negative 0.25 and 0.25, this right here, there it is. Okay, so that's exactly what we're seeing back here. And so what I have is the velocity, and I've got the black as the position. And now watch as we play this. There's the block up, down, back up again, and then it stops. So at 3 pi, it stops up at the top. That's exactly what we just saw in that graph. Now another thing that I want you to notice, as the velocity function is above the axis, the position is increasing because velocity is positive, so we're going up. When velocity falls below the axis, okay, the velocity is working in the negative direction, so we're pulling back down. So the block should come down. As soon as the velocity comes back above, our weight should be increasing. So watch this. Okay, let's go back. As the red line stays above the axis, the black line will increase. And when it goes below, we decrease, and above, we start increasing again. Okay, so we see this kind of lagging result between the two functions, and really what's happening there is we've got a shift between the two functions because we know that cosine and sine are just shifts of one another. Okay. Let's go back up and take a look at some more of these things. It says, when does the block move through the origin for the first time? So when does it come back through the origin? Well, the question is, when is the position 0? So to answer that question algebraically, what we would do is we'd say, when is this guy equal to 0? So let me erase some of this over here, and I'll answer that question for you algebraically. Now, it's nice to be able to have a graph, but it's more important to be able to answer things out algebraically. So let me move this stuff back around here. So the question that's asked is, when is s of t equal to 0? So that's negative 1/4 cosine t. When is that guy 0? And here's where you're solving your trigonometric equations is important. Okay, so multiply both sides by negative 4, and we get when is cosine t equal to 0. And we know that cosine has a 0 value at pi over 2. So if we go and we look, okay, at, let's see if I can go back a little bit here on this. I don't know if it'll allow me. There it is. Okay. So at, I moved it. Okay. At pi over 2, okay, the velocity is still positive, okay, but we've reached the block has come back to its initial position. So it got moved down, and then it popped back up to a position of 0 at pi over 2. And all I did was I solved this equation, set equal to 0. So what we can do, and if you go ahead and you look down here at the solutions, we see that the block initially moves in the positive direction, and it reaches a position of 0 when the time is pi over 2. That's exactly what we just said. Okay, let's go back and answer the last question. It says, when does the block reach its highest point for the first time, and what is the position at that time? Well, clearly the block reaches its highest point right here of 0.25. Now the question is, when does it reach that at 0.25? Well, what we do is we take we ask what t value gives us a height of 0.25. So we know that s of t, which is right down here, is this guy. And we want to know when is it equal to 0.25. So we multiply both sides by -4. And now we ask what angle has a cosine value of -1, and we know that that is pi. So if we go back and we look at pi, whoops, it's so tough to get this thing to go right in the right spot here. I'm going to use my mouse. Okay, at pi, this is the position. The block has reached its highest point, okay, and the velocity is now at 0. Now the velocity will go negative, the block will fall back down. We can do the same thing. When does the block return to its lowest point? The block comes back down to its lowest point here at 2 pi. You can solve that algebraically by figuring out when is your function, this guy right here, when is it equal to negative 0.25. And of course, you can go ahead and you can read that, the information here, the solutions are right down here. So here's our value of pi that we just found, and then of course we can find that same value of 2 pi. What I would like you to do on your own is work through example number 3. So try this skydiving example. We've got a piecewise defined function. See if you can figure it out, and then of course you can go ahead and you can check the solution. Make sure that you work things with your calculus. Okay, make sure you're using your integration techniques to go ahead and solve that over this value. If you can't figure it out, again, please let me know and we'll work through it.